The purpose of this clinic was to test various methods of SNR estimation using the Kepstrom feature vector. There are multiple feature vectors that can represent a person's speech. We just chose the Kepstrom feature vector for this particular clinic. And the overall goal was to determine which method had the lowest estimation error. The motivation behind doing this was to find something that could reliably estimate the SNR of a noisy speech utterance and incorporate this into a speaker identification system. If you know how much noise there is in a speech file, you can determine how much signal processing or conditioning needs to be done in order to have the speech file you're looking at better become cleaner and be more easily able to be compared to another person. In terms of standards, we used a database of speech files created by Texas Instruments and MIT, and we used different speech files to train and test our various methods. In each case, we used 450 speech files, which represented 90 people saying 5 different things. For constraints, the main constraint was computer processing power. We used a lot of speech files, which took a while for the computers to process, and towards the end of the spring semester, we eventually started moving towards Rowan's computational cluster to better handle these constraints. In terms of software, we used MATLAB solely. For this clinic, we looked at vector quantization, or VQ, with soft decision making, a Gaussian mixture model with an expectation maximization algorithm called GMM-EM with hard and soft decision making, and sparse representation via L1 norm minimization. Soft and hard decision making, the difference is hard decision making you use the single best result, whereas soft decision making you use multiple of the best results. This flowchart shows the overall process for the clinic. We trained the models on speech files with white noise added to make SNRs from -1 to 32 decibels. We tested the models on speech files with white noise added to make SNRs from 0 to 30 decibels. We then evaluated the results with the hard or soft decision making, and then if the results weren't that good, we analyzed the code and looked for possible errors in the math we used. VQ training generated codebooks which represented the Kepstrom feature vectors of the training data. These were generated using the Linde-Buzot-Gray algorithm, which is also called binary splitting. The SNR estimation was based off the squared Euclidean distance between the Kepstrom vectors of the testing data and the various codebooks. We said that the smaller the distance, that was a better estimation of SNR, and the larger the distance, the worse estimation of SNR. For vector quantization soft decision, we used the 3 smallest distances and their associated SNRs. We used a weighting function shown below to favor smaller distances. For GMM-EM analysis, we used the NetLab toolbox available online at MATLAB's website. The training generated a single structure containing 34 Gaussian mixture models, which represented SNRs from -1 to 32 decibels. For testing, we looked at the probability that the frames of the test speech files matched the SNR of the model they were being compared to. We could multiply all the probabilities together to create a probability that the speech file matched the model, but instead we took the logarithm of the probabilities and summed up these logs to create a score, because if you remember the log rule is the log of things being multiplied is equivalent to log of each individual item being summed. So this sum represented a score relating the test data and the models, and the higher score created a better match and the lower score indicated a worse match. When one of our speech files had 29 dB SNR and it was compared to the 29 dB model, as you can see in the bottom right of the left figure, the score is positive and very high. Whereas when we compare the speech file to a 5 dB model, if you look in the bottom right of the right-hand figure, the score is very negative. And this shows that there is great distinction between the scores of matching models and incorrect models. For GMM-EM estimation, hard decision used the single highest scoring model and said that that model's SNR was the SNR estimate of our speech file. For soft decision, we took the 3 highest scores and used them and their corresponding SNRs with a weighting function. First, we convert the scores back to probability. Then we normalize the probabilities to the total of the sum of the 3 probabilities used. And then we computed the SNR estimate by weighting the SNRs. And you can see the math shown below. The chart on the left shows the results of the VQ soft, GMM hard, and GMM soft estimation method testing. The x-axis shows the SNR that the test speech files were at in decibels. The y-axis shows the average absolute error of the SNR estimation at that specific SNR. All 3 methods follow similar trends, but the GMM soft has pretty much overall consistently smaller errors. The overall average absolute errors are shown in the table. These are the averages of the average absolute errors of the SNR estimation method. As you can see, VQ soft and GMM hard both have roughly 1.8 decibels in overall error, whereas the GMM soft method has about 1.6 decibels in overall error. For all 3 methods could be used to estimate SNR within a reasonable amount of error, but the GMM soft method has less error than the other 2. For sparse representation via L1 norm minimization, we started investigating this about 1 month left in the semester, and we are looking at sparsely representing the vector x in the equation a times x equals y. A is a matrix of all our codebooks from VQ training concatenated vertically and then transposed, and y is a row of the Kepstrom feature vector of a noisy speech file. So essentially we're trying to create a linear combination of now columns of the A matrix to represent y. And we solve for x using the constraint of minimal L1 norm, and we do this through using a convex optimization toolbox called CVX. Solving the system for x once doesn't provide good results, so we use a method shown below to essentially guess where the correct zeros are, and each time we go through and guess where they are, we store the value of x, the magnitude of it, and then over time we continuously add the new solutions of x to our stored values of x. And the goal through doing this is to identify a single index of x, or perhaps a cluster of indices, and use them to estimate the SNR based on their location and the relationship in terms of the length of the codebooks. So unfortunately at this point conclusive results haven't been reached for sparse representation methods, so we moved our work to Rohn's computational cluster to speed up the process. However, the CVX toolbox has licensing limits, which limits the number of nodes we can use it on. This was sort of worked around by coordinating with other clinic group members to make sure there was minimal overlap. But still, due to the large size of the data in the codebooks, a single noisy speech file can have a number of iterations on the order of about tens of thousands. So when you extrapolate this runtime to 450 speech files at 31 SNRs, it can add up quite quickly. Additionally, we're looking at switching up the equation we're using to, instead of doing a times x equals y, moving towards a times x minus y is less than an epsilon, where epsilon represents an error bound, because the exact equality may have been too constraining on the solver. That concludes the video. Thank you for watching and listening.